Hi everyone. Alright, we are kind of moving away from trig. So fight back those tears. And we are moving toward, for a little bit, rational functions and their graphs and such. We did a lot with the algebra of them early on in the year. Just the adding rational functions and rational expressions and things like that. But now we are moving on toward what the graphs look like. And we're talking about, today, our focus is going to be on asymptotes. On the next video or two after that, we will incorporate this into the graphs when we're actually going to make the graphs by hand. So, but I was also saying we will spend a little bit of time on this. We'll spend a little time on logarithms, and then I think we'll pretty much be done with what we have to do this year. So let's first of all start with rational functions and the definition. A rational function is a quotient of two polynomial functions. A polynomial over a polynomial. N is a polynomial, n of x is a polynomial, d of x is a polynomial, n on the top for numerator, d for denominator, kind of a clever thing there. And this is kind of a abstract version, but you've got this, we need to talk about this term right here, a sub n. It's the lead coefficient. Here's the x with the highest power. N would be the degree of this polynomial. M would be the degree of this polynomial. The lead coefficient of this one is b sub m. Alright, it's just a number in front of the variable with the biggest power. And we need to talk about those. So this is a lead coefficient, this is a lead coefficient. The degree is the highest power, which is n. Notice that all these go n minus 1, and then you keep going down until you get x to the first. And then this is your constant, which is x to the 0, but we don't write that. And so on. Alright, so here is an example of a rational function. The numerator function is 3x. The denominator function is x plus 1. They're both degree 1 polynomials. Now, I have this ready, I think. Yeah, if we look at the graph of this. Now, I want you to take just some notice here. Like right around here, the graph will go up real fast here, and if you're going from the left, it goes down real fast. And it seems like it's surrounding this negative 1 value on the x-axis. And also, I see something right here. 1, 2, right around 3 here. It looks like on the left side it gets close to it, and on the right side, the end behavior is that. So as you go, looks like the end behavior as x goes to negative infinity is 3. Looks like y will be 3. And the end behavior as x goes to positive infinity is also 3. And it approaches it from the bottom on this side and from the top on this side. So if I just were kind of think of what we were seeing there, looks like 1, 2, 3, 4. 1, 2, 3, 4. Notice we were talking about how we were kind of around there, and 1, 2, 3, kind of around here. That if you recall what you were seeing there, and if you don't, you can put this on your calculator. It was kind of doing this, and then it was kind of doing this. Okay? What's actually happening here, this is called an asymptote. And this is a vertical asymptote. And I'll just write VA for vertical asymptote. and it looks like x equals -1 is a vertical asymptote. Now, we do call this a horizontal asymptote, although technically it's just in behavior that we're talking about here. But we will call it a horizontal asymptote because it approaches here, it approaches here. We did that with our trig a little bit. Remember the tangent functions? We talked about asymptotes. This looks like y equals 3 is a horizontal asymptote, just from the graph. Now, just without the graph, maybe algebraically, if we had to find a vertical asymptote, the way you find it is you will solve the equation where the denominator, solve for x, d of x equals 0. So, just in words, set the denominator equal to 0. And solve for x. That is how you find the vertical asymptotes. So if I look at this one, x plus 1 equals 0. If I solve, I get x equals -1. And that's that line right there. That's that horizontal, nope. That's that vertical asymptote. Okay. Now, vertical asymptote is pretty easy to find. You set the denominator equal to 0, solve for x, and you've got your vertical asymptotes. But you have to account for 3 different situations. You just got to figure out which situation applies when you're trying to find horizontal asymptotes. Now, if you'll remember from the other page I had, last page, n is the degree of the numerator, m is the degree of the denominator. In the case where n equals m, the line y equals the lead coefficient of n of x over the lead coefficient of d of x is the horizontal asymptote. In the problem we had 3x over x plus 1. Yes. We had y equals 3x over x plus 1, and the lead coefficient is 3. The lead coefficient here is 1, so y equals 3 over 1, or just plain old 3, was our horizontal asymptote. And if you go back and look at the graph we had, look at the graph we have here, that kind of confirms that. 1, 2, 3. If I draw this way, and actually I'm not going to do that right now. I've got other functions in there. Okay, so if the degree of the top and the degree of the bottom are the same, this is what you do. You just put the lead coefficient over lead coefficient, and y equals 3. That is your horizontal asymptote. If you have the degree of the numerator is smaller than the degree of the denominator, then your horizontal asymptote is y equals 0, or it's just the x-axis is the horizontal asymptote. That's when the degree of the top is smaller than the degree of the bottom. If you have a case where the degree of the numerator is greater than the degree of the denominator, then you have no horizontal asymptote. Okay, I'm going to go to the next video. I'll stop this video, and we're going to do 3 examples on the next video.